Welcome back to Securing Digital Democracy. This is a very exciting lecture for me because while last time we got to talk about some of the problems with DREs in concept, some of the things people thought might go wrong, in this lecture I get to show you some of the things that go wrong. We're going to get to go through a series of research projects where researchers were able to get a hold of DRE voting machines actually used in the real world and get them to misbehave in ways that simulate what real criminals could do. The first of these stories comes from my own work when back in 2006, when I was a grad student at Princeton getting my PhD, I got to be part of the first hands-on academic study of a DRE used in real elections in the United States. Here's the voting machine that we got to look at. It was the Diebold AccuVote TS. This was at the time the most widely used electronic voting machine in the US. It's still used statewide in Maryland and Georgia. The AccuVote TS is a touchscreen machine. It's actually very similar to a computer. So conceptually, there's no difference between the voting machine and the computer. They both run arbitrary software. They both have internal flash storage. They both have a flat panel display. The only difference, conceptually at least, is in the cosmetics. The Diebold machine has a touch-sensitive screen, unlike your typical laptop, but really it works very similarly to an iPad or a tablet. On an architectural level inside, it's actually a little bit more similar to a PDA or a smartphone. It uses a microprocessor that's designed and was used at the time for devices like this, and it runs a version of Windows called Windows CE, which is a little bit different from your desktop operating system, but was designed for PDAs and smartphones. So the Diebold machine that we acquired came to us from an anonymous source. Because you'll recall at the time, as we talked about at the end of the last lecture, Diebold was very, very protective of these machines. They had non-disclosure agreements with all of their customers. They threatened election officials who wanted to work with independent security evaluators with losing their jobs. It was a very cloak and dagger time. And I told you at the beginning of the course how I went up to New York City and received the machine from the trench coat wearing man with the leather briefcase. But the cloak and daggerness of the whole thing continued. We ended up spending an entire summer working on the machine in total secrecy. We didn't want Diebold to rush off to try to get, say, a court order for us to stop the work. Although our lawyers assured us that the process was completely legal, we didn't want it to be tied up in litigation for an extended period. So our plan was to perform our study in secrecy and then go public with it. At the same time, the voting machine manufacturer would learn about the results. As a result of this, we spent the summer working on the machine in the basement of the Friends Center at Princeton in an unmarked room that wasn't even on the maps of the building. This is the level of cloak and daggerish secrecy involved. So our first task was to find out how the machine worked and to be able to get a copy of the software out of the machine. Now, you think about this, if you're handed a computer device that's what we call an embedded system, that's a device that's made with special purpose software that's stored inside it, it's not entirely clear how you would get the software out at all to even begin looking at it. So we opened the machine, and the first thing we did was try to understand how the hardware worked. Now, by looking at the chips, we were able to identify the parts. Here's the microprocessor. These are the memory chips, the flash chips that store the machine's internal software and a record of the votes. This is a slot for a PC card, a kind of removable memory card that's basically the same idea as in your digital camera. Now, election officials used these cards to program in the ballots at the start of the election and then to copy out the votes for each candidate at the end. They'd take the card out and bring it to a central location where they'd be electronically tabulated by a different kind of computer. In addition to those, there was a socket with a removable memory chip. This removable memory chip ended up being the way we were able to crack the software and figure out how to copy it off. But I'll tell you a little bit more about how that works in a second. To understand how the software behaved once we did copy it off of the machine, we had to go through a process called reverse engineering. And reverse engineering is a standard technique in computer science where you start with a completed device and you go backwards to find out how it works. In the case of software reverse engineering, we're starting with a finished piece of computer software, and we want to try to go backwards and understand what's in the source code to that software. Typically, computer software that you receive isn't in the form of source code, the actual instructions people have written. It's in the form of what we call a binary. That is an executable computer program written in a much more compact form of instructions that are built for computers to understand, but not for people. It's possible to reverse that process, to go backwards from the executable or binary to something resembling source code by using very specialized computer software like this. This is a package called IDA Pro that's a system for reverse engineering software. The process of using this is extremely tedious. It might take weeks to go backwards for a software the complexity of this voting machine. But the process is, in concept, not that hard to understand. The IDA will display for us here the set of compact computer instructions. This is something called assembly language. And we can add comments as we're trying to decipher what each line is for. It also shows branches every time the software might take different paths depending on the state of the machine. So little by little, we can work backwards from the computer instructions and get to something that is a human understanding of what the software is doing. After weeks of this, we finally got the machine into a configuration where we understood how it worked and could run a simulation of a real election. Some things we found from reverse engineering that software were really, really disturbing. We found a number of design flaws that could allow someone who had even temporary access to that memory card used to load ballots into the machine to replace parts of the software that were running the election. The software in the AccuVote TS has three main layers. At the bottom of this software stack, as we call it, is something called the bootloader. And the bootloader is very low-level, simple software that's responsible for turning on the machine and starting up the operating system. The bootloader runs Windows. That is, it starts the Windows operating system. And the technical name for what it runs is the Windows CE kernel. On top of Windows, the first thing that Windows starts is an application called Ballot Station. And Ballot Station is actually not that different from a program you might run on your desktop PC, like a word processor or a web browser. Except that instead of providing those kinds of features, it provides screens for setting up an election, voting, and then outputting the results of an election at the end of the polls. Now, we figured out when we were reverse engineering the machine that there's some design flaws in the bootloader that could allow a malicious person to replace any piece of this software with their own tampered-with version. Now, even if we assume that the Diebold software that ships with the machine normally is honest, we have to worry that someone who replaced the software with a tampered version might reprogram it to be malicious and to change or steal votes. Now, what we found was that the bootloader, by design, has features for updating the machine's software if certain files are present on the removable memory card used to load the ballot design at the beginning of the election. If there's a file with the name fboot.nb0, the bootloader will, when you turn on the machine, just replace itself with whatever's in that file. Another file named nk.bin will cause the bootloader to replace Windows with the contents of that file. And through another process, a file called install.ins can be used to replace the ballot station software. Now, it's important for voting machines like any other kind of computer to have some mechanism for doing software updates. But the problem with the Diebold machine was there weren't any security controls on the way this worked. All you had to do was know the file name. There weren't any secrets necessary for that process. There wasn't even any confirmation on the screen asking whether you wanted to do that update. Another file called explorer.glb, if present on the card, would cause the machine not to automatically run Ballot Station, but instead to run Windows Explorer. This is basically the same interface you get on a desktop PC for browsing through the files. So this was immensely helpful to us in figuring out how the machine worked and in testing on it. But it could also provide another means of replacing software. You could just start Windows like this and then copy your malicious voting software onto the machine from the removable card. Another means of potentially subverting the software on the system involved that removable ROM chip on the motherboard. And I have one of those chips right here. So this was a feature that was built into the machine probably for testing while they were designing it. If you set some switches or jumpers on the motherboard to the position shown in that table, it can cause the machine to start not from its internal memory bootloader, but from whatever software is on this removable chip. The machine came with one of these chips that had one version of the software, and we started out our whole process by reverse engineering that software and modifying it to give us further control of the machine and allow us to dump the rest of the contents of its internal memory. So all we had to do was program our own chip with our malicious software, change some jumpers, and plug the chip in and turn it back on. So this is an example of what I call a failure in depth. There wasn't just one route for replacing the machine's code with malicious software. There were 3 totally separate routes that someone could go through. If any of these were available, an attacker could tamper with the machine. There was booting into Windows. There was using those magic file names on the memory card to replace the internal software or firmware. And there was replacing the ROM chip. This sort of problem with multiple failures giving an attacker multiple options for breaking into a machine is something we're going to see again with other sorts of voting systems in the future. Now it's time to ask what could go wrong. You've seen different ways that someone could replace the software, replace the ballot station application with their own malicious version. Now I'd like you to think about some of the different kinds of attacks that someone could do if they were able to get malicious software on the machine. We'll talk about some of the things that we actually tried in the research project when we come back. If the attacker can change the software on the machine, there's almost no end to what sorts of malicious tampering he can do. The most obvious desire would be to change the votes stored on the machine. But there are a few ways you could go about doing that. I'm going to explain the mechanisms for cheating that we actually demonstrated in the research project. We developed an application that can be loaded onto the machine by exploiting any of those design flaws I talked about and runs on top of Windows alongside the ballot station interface. It hides in the background, so there's nothing normally on the screen unless the attacker invokes a special control screen that gives them an option to set the election result. Using this interface, you can pick who's going to win and by how much. The stuffer application will then continue to hide in the background, and as it runs, it monitors the voting process. Every time someone casts a vote, the stuffer program determines whether that vote should be changed in order to make the final election outcome match what the attacker has programmed. So the AccuVote has actually 3 different records that reflect what's going on during voting. In its internal memory inside the case, there's a primary vote record and an audit log. And then on that removable memory card, the machine stores a backup vote record. All of these are accessible from software running on the machine, including from the stuffer. So our stuffer application changes the records in all three of these places. At the end of the election, the stuffer can remove itself, and having changed all of the records, there will then be no electronic evidence left in the machine that anything was amiss. This is a great illustration of the problems with fully paperless DREs. If all of the records are electronic and all of them can be modified from the software, then if that software is malicious, it can make things go wrong. So the test election we ran with this was a contest between George Washington and Benedict Arnold. And what we would do, we would load the malicious software onto the machine beforehand using that removable memory card. Then we would have the machine print out its initial paper tape. This is a standard procedure at the beginning of an election. They'll print a tape where the machine checks that it has 0 votes. Of course, when you think about what's really going on with a 0 tape like this, the software is just driving the printer and printing whatever text the software says. So our malicious software could very easily just have this tape print 0 votes, even if there were votes loaded in. So nothing appears to be wrong at this point. Then voters can cast their votes, and we'd always have everyone vote for George Washington. But no matter how many votes were cast, the output of the election would always be Benedict Arnold winning. This is our malicious software at work, actually functioning in the real machine. As if this attack weren't bad enough, it turns out that we can exploit these same problems to do something that's even more dangerous than just simply infecting one machine via its memory card. In the process of conducting a normal election, the election officials take the memory card that looks basically like this, and they will move it from machine to machine in order to do things like performing software updates. So they'll put a card into the first machine, take it out, put it into the second machine, and so on. This moving a card from machine to machine is a vector for spreading malicious software. Just like back in the days of floppy disks, we had to worry about disks being infected with viruses. We realized that this transfer of the memory card might be exploited in a similar way. What we came up with was a way to make a voting machine virus. That is, a way to infect a single machine with malicious software that would then spread via the memory card as it was moved from machine to machine. So you put the memory card into the infected machine, the card becomes infected. Then if you put the card into another machine, that machine becomes infected. In this way, it would be possible for a voting machine virus that was loaded onto a single machine by someone with very temporary access to that machine or just a few seconds of access to its removable memory card, and then to spread through the course of an election cycle or two to all of the other machines in the jurisdiction. So you could imagine infecting a whole state from a single point of entry by spreading a voting machine virus. Now, this is just tremendously scary because it reduces the size of the conspiracy you need to attack a statewide election to potentially just one technically expert person and access to one memory card or one voting machine. Actually, Diebold did have one defense mechanism in place, and that was a physical security mechanism. Covering the memory card slot on the side of the machine was a locking metal door that you had to get open in order to replace the card. This turned out to be another example of a failure in depth, but before I tell you how the door mechanism failed, I'd like you to try to puzzle out for yourself what could go wrong with a lock and key mechanism like this. So it turns out that there was a lot that was wrong with the lock and key used to protect the AccuVote TS. Diebold made several different mistakes. The first problem was that all of the voting machines everywhere used the exact same key, including all of the machines in the state of Maryland and the state of Georgia. So if a criminal were to steal one of those keys, could then go and open up any of the voting machines. As if that weren't bad enough, you didn't even need the key to open up the machine. It turned out the lock was easy to pick. I can pick the lock on the AccuVote TS in about 10 seconds with some lock picking tools, or I've taught students to open a lock like this in less than a minute using only some paper clips. If you know what you're doing or take a few minutes to learn, this lock doesn't pose any kind of hurdle. As if that weren't bad enough, it turns out that the same key was already widely available. There's a number written on the side of the key, and if you put that into Google, you'll find the exact same key is widely sold on eBay for things like jukeboxes and hotel minibars. Low security applications like this are using the same standard kind of key. Diebold selected a low security and widely available key for the TS. And I actually bought one of those keys on eBay. Here it is. This was sold for a jukebox, and it successfully opens the voting machine. As if that weren't bad enough, Diebold themselves had a website where people could buy the key. Now it wasn't as bad as you might think. Diebold's website would only sell you the key if you had already bought voting machines from them, so you had to be a municipality. But they did have this catalog page that had a very high resolution picture of the key that in this video I'm partially blacking out. The picture was high enough resolution that a reader who learned about our work and saw this web page was able to go to the hardware store and buy a similar looking key and then go home and file it down to match the picture. He sent us the key that he cut at home from the picture, and it opened the voting machine. Here's the actual homemade Diebold key. So Diebold on their own website was giving out all the information you needed to defeat the physical security mechanism, which was the only thing that was keeping someone standing at the machine from replacing its software. So this is another example, the Diebold key of a failure in depth. You could steal a key from another machine, or pick the lock, or buy one online, or make one at home. Any of these ways would have allowed you to get into the machine. So the attacker had multiple options because of Diebold's design flaws. Now we might ask whether the Diebold machine was particularly bad with these multiple failures in depth, this ability for malicious software to change the votes, or for a voting machine virus to spread from machine to machine. Was it just a Diebold problem, or is this something that affects other DREs too? We'll get to see the answer to that question in the next segment.